So we dedicated a big chunk of these lectures to understanding how heat transfer occurs within solid objects, a mode of heat transfer that we had called conduction. And we dedicated a lot of time to trying to understand or model how heat transfer occurs between solids and fluids, or between fluids, a mode of heat transfer that we had termed convection. But throughout the entirety of these lectures, we've been avoiding this kind of mysterious third mode that we had hypothesized back at the beginning of these lectures. This third mysterious mode of heat transfer, which is called radiation. Now, as a reminder of what we hypothesized radiation was, we said that radiation was the mode of heat transfer that governed what happens when you take two, say, rocks that have different temperatures and you put them inside of a vacuum chamber. And inside of that vacuum chamber, there's no matter, right? There's no air, there's no fluid, there's no nothing between these two separated rocks. And then we would observe that, absent any kind of like weird heat sources or heat generation, that over time, the temperature of these two rocks would eventually become the same, even though there's no intervening matter. Okay? So that's what we had called radiation. And the issue is that we never really developed a model for how radiation, for what radiative heat fluxes are. Now you might say, well, I mean, that's no biggie. We can just use the equation for modeling heat transfer between two different objects, right? The Q double prime is equal to H times delta T, and then we're good. And that's a good idea, so to speak, but that equation is a little bit too inaccurate when trying to model radiation, but it also critically heavily undermines the complexity of the physical process that radiation is, or at least what we think the physical process of radiation is. And the best way to illustrate that is to talk about the radiative system that is perhaps the most important to our day-to-day lives as human beings, which is the sun and the earth. All right, so we believe that the sun is this big ball of plasma, and a bunch of chemical and physical reactions occur within it such that it emits light and hypothetically maybe heat that it's shot off into empty space. And some of that light and some of that heat hits the earth, and then that gives us enough light to be able to see things, to have vision. And it also gives us enough heat to be able to be at a comfortable range of temperatures that we can exist in, rather than the very chilly 4 degrees Kelvin of, empty space. But if we think about this statement a little bit, too much, we start to notice that there's a fundamental flaw in it, okay? If it's true that thermal energy is moving around, right, that's being emitted by the sun and transferred to the earth through the medium of empty space, well, what is that thermal energy, right? What is the thermal energy of a chunk of empty space? And we can use the equation that we had derived near the beginning of the course to state that, right? Where we can say that the thermal energy of any object, right, including nothing, I suppose, including the void, we had said was its specific heat capacity times its density times its volume times its temperature. And so if you think about it, right, if this is the thermal energy of, or approximately the thermal energy of a chunk of empty space, the mass density of empty space is 0, which means that the thermal energy of empty space is 0, independent of whatever, the temperature is, whatever that may mean, however you define that. And so if there is no thermal energy in empty space, how on earth can thermal energy, no pun intended, by the way, how on earth can thermal energy be moving through empty space if it's just 0 everywhere? How can heat actually be transferred from the sun to the earth? And the answer is that technically speaking, it's not. There is no heat transfer that's happening in empty space, okay? And it's crazy to say that because we know that the temperature of the sun and the temperature of the earth are linked, right? That we are the temperature that we're at because the temperature of the sun is where it's at. And how does this actually occur? Well, it's because of the other thing that the sun provides, not heat, which we said it can't do because heat doesn't transmit through empty space, light, okay? In other words, electromagnetic energy. And electromagnetic energy does have the ability to move through vacuum, right? Light has the ability to move through vacuum. And so as a result, the thing that we call radiation, the process of radiation, actually consists of two different things, which combined represent the experimental, hypothesis of the process of radiation, which is that the sun, or any object that has matter, engages in a complicated process via which its thermal properties govern some sort of emission of electromagnetic energy. So we call the process of emission the process via which the thermal properties of an object generate electromagnetic energy fluxes that then travel through empty space. Those electromagnetic energy fluxes in the form of light, right, because that's just what it is, reach the Earth or any body that has matter and engages in a physical dance in which some of that electromagnetic energy is converted into thermal energy, right, into heat. And the process via which that happens is called absorption. And so when we discuss radiation as a mode of heat transfer, we're actually discussing two different things. We're discussing the process via which thermal energy, technically speaking more like thermal properties, are converted into electromagnetic energy, and then the way in which that electromagnetic energy is converted back to thermal energy. And somehow this song and dance will allow us to observe or explain the fact that objects which have temperatures that are different in vacuum will eventually equilibrate to the same temperature. This doesn't occur, by the way, between the sun and the Earth simply because of the fact that the sun is generating thermal energy or what have you, by converting the chemical energy of the constituents of the sun into stuff. So from a thermal perspective, this is a forced system. This is continuously generating, energy, okay? But eventually, over, billions and billions of years, we'll find that that chemical energy runs out, and then the sun eventually will undergo its dying process. And so really, in actuality, at the end of the solar system, so to speak, the temperature of the Earth, or whatever's left of it, and the temperature of the sun will in fact be the same. Interesting to think about it. Not something we have to worry about though. Anyways, so the thing that I want to talk about now, at least for the duration of this lecture, is to characterize this electromagnetic radiation, this electromagnetic energy, what we call light, and to talk a little bit about how we characterize the emission of light from an object as a function of its thermal properties. Okay? So let's talk about light. Light can be characterized in terms of one of two properties, both of which are interlinked in a mechanism that I'm going to show you in a second. But the idea is that we can describe light, or different kinds of light, using either wavelengths or frequencies. So we can differentiate between two different kinds of light by saying that one has a wavelength of this and the other has a wavelength of that. Similarly, I can say that it has a frequency of this or the frequency of that. Okay? And either of these properties are basically the single property that light is allowed to have. The single independent property that light's allowed to have. Okay? Everything about light is usually characterized by either of these things. And so usually, depending on what kind of field of physics you study, you'll either refer to a light and its characteristics either by frequency or by wavelength. For the purposes of heat transfer, most people study it from like wavelengths. We use the wavelength as the characteristic property, but in physics often you'll talk about frequencies too. So if you see me accidentally mention something about frequencies, just be aware it's my training is leaking in, so to speak. Okay, so these properties are not independent of each other, right? And the reason that they're not independent of each other is because the speed of light in every inertial reference frame is the same. That speed of light, which we'll refer to using the variable c, is always 299,792,558 meters per second, right? And this is just equal to the wavelength of that light times its frequency. And so it turns out, right, that because this speed of light is fixed, that whenever we know the wavelength of light, we of course know its frequency too. They're locked in, so to speak, via this relationship. Now, if the speed of light is a constant, then isn't the energy of light also a constant too? Not quite, because remember, we're not talking about kinetic energy, we're talking about electromagnetic energy. And so in the context of thinking about electromagnetic energy, it's independent, so to speak, of the speed. I shouldn't say it's independent, I should say that it is a function of the speed, but the speed is a fixed number, so it doesn't really affect. The way that we write down the energy of, say, a beam or a ray of light that's at a specific wavelength is via the following. We say that its energy is equal to this physical constant that's called a Planck constant. It's just a universal constant, it's a single number, multiplied by the speed of light divided by the wavelength, okay? And so whenever we have information about the wavelength of a beam of light, assuming that that light only has one wavelength, we can determine its energy just by knowing the values of this Planck constant and the speed of light, which again are just universal constants that you can find in any physics book. Importantly, what we observe is that the smaller the wavelength, the larger the energy, okay? And so you expect that the interaction between light waves and us, objects, becomes more and more significant, more and more impactful, the smaller the wavelengths get. And so the way that we categorize light, although there isn't like a, I would say, specific range that everybody uses, there is kind of like a set of ranges of wavelengths that we give special names to based off of what we use them for, but also in terms of their interactions with us, with the human body and with objects, okay? So for example, radio waves are waves of light that have any frequency, or pardon me, any wavelength on the order of about 10 to the 3 meters or larger, okay? We consider these wavelengths to be relatively large. When we plug it into the equations, we find that the energy of radio waves is small. So small that they usually don't interfere with bodily processes. The chances of a radio wave actually even interacting with the human body is very, 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 very small. And that's why we use radio waves for communication so much. We permeate the earth with radio waves because of the fact that, one, they allow us to communicate with each other, but they also are the frequency or wavelength of light that has the least chance of actually interfering with our bodily processes in our health, okay? So anything around 10 to the 3 or larger, roughly speaking, is the radio frequencies, or the radio wavelengths, I should say. Anything that has a frequency in the order of, a wavelength in the order of about 10 to the minus 2 meters, that starts to be what we call the microwave range. And this is a very broad, between radio and microwave, there's a very broad, spread of wavelengths, right? It's 5 orders of magnitude. And so where microwave starts and radio ends is kind of, it's not exactly like a fixed thing, but nevertheless, microwaves range from the sort of stuff that we use to have our computers communicate with the internet, right? Wi-Fi. On the lower end, on the larger end of the wavelengths, and then towards the smaller end of the wavelengths, towards the high energy range of microwaves, well, we use the microwaves that show up when cooking your food inside of an aptly named microwave. That's how a microwave works. It emits electromagnetic energy in the microwave wavelengths, which is absorbed into thermal, or transformed into thermal energy upon absorption and then heats up your food, okay? As we start going further and further down, right, we call infrared the stuff that's roughly around the 10 to the minus 5 meter range in terms of wavelengths. And infrared is interesting. It's very interesting for a couple of reasons. We'll get to those in a second. But ultimately, the reason that infrared is so important is because it is the wavelength of light, or the set of wavelengths of light, in which it's the flavor of light that our bodies like to absorb the most from the perspective of thermality. Right? We convert infrared light into heat better than probably any other wavelength of light. And so infrared matters a lot from the perspective of heating and cooling via radiation on Earth. Okay? Once we start getting to smaller and smaller wavelengths, we actually get to light that we can see. And so there's this narrow band of wavelengths in the electromagnetic spectrum, which is the visible spectrum, centered roughly around 0.5 times 10 to the minus 6 meters. Okay? And so, of course, this contains red, orange, yellow. All of your favorite colors are inside of a tiny little narrow band centered around 0.5 times 10 to the minus 6. So in the slightly submicron range. Okay? After we get smaller and smaller, we start hitting UV. Okay? And UV is light that we can't necessarily see. Okay? Now we have energy, or pardon me, we have wavelengths that slowly and slowly became small enough to the point where now those wavelengths of light do interact with matter, either via a process of heating or either by allowing us to see things. Once we start hitting UV, the interaction that happens between these wavelengths of light, or these types of light, stops being helpful and begins to be hurtful, because the energy of UV is sufficiently large that when it interacts with our skin, at least in prolonged exposure, it actually has enough energy to start breaking down, to start destroying the cells in our skin, okay? If you expose yourself too long to UV, you get a sunburn, which is technically named correctly, but it's not quite a burn in the sense that it's not so much that the temperature of your skin increased so much that it caused thermal damage. It's actually that the literal electromagnetic radiation has so much energy that it destroys, pieces of your skin. So UV, like sunburn, is much more of a proper radiation burn in the Chernobyl sense than it is an actual thermal burn. As you start getting into smaller and smaller wavelengths, of course, now we start seeing familiar terms when it comes to harmful radiation. X-rays are just light, which have wavelengths of on the order of about 10 to the minus 10 meters. And X-rays, of course, are harmful if you expose yourself to them continuously. It's okay to get small doses of them if you, for example, go and get an X-ray at the doctor. But you definitely don't want to be in a room where you continuously get exposed to X-rays, because, of course, it starts to damage the cellular structure of the parts of your body, which leads to an increased risk of cancer, among many other things. And then, as you start going further and further down, anything that's on the order of about 10 to the minus 12 meters or smaller is what we call a gamma ray. Okay, so gamma rays are just light, and you definitely do not want to be exposed to gamma rays. But the point is that we characterize light in all of these different flavors because the way that we use them, the way that they interact with our bodies, is different based off of their wavelength and, by extension, their energy. Okay? So this tells us something about light. Now that we've discussed a little bit about what light is, we know that this light is an electromagnetic energy, a form of electromagnetic energy that is transferred through empty space. So how do we model the rate at which that electromagnetic energy is being transferred? What's the right equation to use? Well, the quantity that we would like to use is a quantity that's very similar to the one that we constructed for our two previous models, which is just a flux, right? Energy flux. And so we can create although the usage of the variable is a little sketchy, it's nevertheless commonly referred to using this variable, we can create a Q double prime that no longer represents a heat flux. It now represents an electromagnetic energy flux. Okay? And so we would write this as a function of something else. But here's the problem. Most objects emit, like the energy, the electromagnetic energy flux associated with a given object isn't just like some number. It doesn't actually make sense for us just to use something that has units of watts per meter squared to fully characterize the electromagnetic emission of an object, because that doesn't give us enough resolution to understand how it behaves. There has to be something else that we can use to kind of increase the resolution of this. And so what we'll wind up doing is we'll actually wind up breaking down this energy flux into pieces, all right? Such that this is the integral of a much more, I guess, complex thing. So what can we break this down into? Like what is this affected by? Well, notice that most objects don't emit electromagnetic energy at a single wavelength. The sun emits visible light. It also emits UV, which is why we get sunburns. It also emits infrared. It also emits radio waves. It emits all of those. And so as a result, it turns out that the way that we have to characterize the emission isn't just as a function of a single energy flux, but that the way that this energy flux looks like depends on the sum of the fluxes that come in from every wavelength, right? Every frequency or whatever of light that is being emitted off of the object. And so it turns out that we have to break this down in terms of wavelength, okay? So this Q double prime rad is going to be the integral of something over a range of wavelengths. Now, is this it? Not quite, because another factor that affects this sort of heat flux, or this energy flux, I should say, another factor that affects this is direction. For example, if I have some kind of point emitter, okay, if I consider how much electromagnetic energy is being emitted from a specific point, I have to consider whether or not that the amount that's being emitted changes if I consider emission in this direction, or in this direction, or in this direction, okay? And so I have to break this down, not just in terms of wavelength, but I also have to break this down in terms of direction. So how do I characterize that? Well, if I use a coordinate system that's centered around the point of emission, and let's say that I wanted to analyze, I don't know, how much of this is happening in this direction, represented by some point in space, right? Then we can characterize this direction by creating a set of angles, which I'm defining currently in the following form. But they can be defined in other ways, such that each of these two angles provides a single direction, right? A single individual unique direction. Okay? And so we break up this energy flux in terms of per wavelength, but also per solid angle, which is the correct way to refer to the fact that we're breaking this up into a direction in 3D space, so to speak, per 3D direction, if you prefer to think about it that way. So the integral that we have to perform here for the wavelengths was over all wavelengths, and here it's over all possible directions, which based off of this analysis is an integral that looks like this and will carry, let me see, I have to make sure I have enough space, will carry some geometric factors in here There we are. So these two things right here are geometric factors. They don't really matter from a physical perspective. They're just important because of the way that we define the angles. And then integrating over these two angular coordinates and the wavelength. And the quantity that is the root quantity, the thing that actually describes the emission of the object, is this thing that we usually refer to as a spectral intensity. Right? This spectral intensity I lambda E, which is named this way or written down in this way because the I represents the intensity part. The lambda just tells us that it's a function of the wavelength. And this E tells us that it's the emitted, right? We're going to see a counterpart of this that's the absorbed, electromagnetic heat flux at a given point, but that's for later. And so we find that this expression is kind of the breaking down of this electromagnetic energy flux into the actual quantity, that is the root quantity that governs the emission, which is the spectral intensity. Now, what is the spectral intensity? And this is kind of funny to state because what happens is that we're not actually barely, at least for the purposes of this course, we're never ever actually going to calculate the spectral intensity of an object, okay? It's far too complex. It depends on so many different possible properties and things in the setup. However, we can estimate an ideal spectral intensity for all objects, which we can use as a kind of conceptual tentpole to allow us to approximate what this is, okay? And what that is called, that ideal object, that ideal spectral intensity, is usually referred to as the black body spectral intensity. The reason it carries this name is actually a bit of a misnomer. It's because of technically three different properties that we hypothesize this kind of ideal emitter has. And it's the following. We say that for an ideal emitter, that it absorbs all incoming radiation. So any electromagnetic energy that comes by and hits it is absorbed into it. This is where the black body part of it comes in, because it's supposed to be that the general way that we see objects has to do with reflection. It has to do with how much of the light that is coming into an object, how much of that gets reflected outwards, and that reflection governs, hypothetically speaking, how much or how we observe a given object. So if this thing is absorbing all incoming radiation, then hypothetically speaking, it's not reflecting any, and therefore it should appear black. But that's incorrect, because what happens is that even though it's absorbing all incoming radiation, it still is obviously emitting radiation. And the nature of the emission will tell us whether or not the body is actually dark or whether or not it's going to have some kind of like visual color that we can discern. Okay? The second thing that we assume is that black bodies are diffuse. And what I mean by diffuse is that the spectral intensity of this body, of this ideal emitter, right, is not a function of the angles. Okay? So it doesn't have any kind of directional dependence when it comes to actually calculating the spectral intensity, right? So there's no dependence on angle. When you do the integral, these two terms will show up, but you won't get anything that's a function of angles in here, right? And the third thing is that, of course, it's ideal. And not just ideal in the net sense, but it's ideal at all wavelengths. So for every wavelength, the maximum spectral intensity is whatever the black body spectral intensity is at that specific wavelength for that specific temperature. So, given all of these things, what is the actual spectral intensity of a black body emitter? That spectral intensity is the following. It's a complicated expression, mind you, but it is nevertheless something that we can write down, and you can find it by doing a relatively complex statistical mechanics analysis of how these sorts of systems work. So if I look at my notes briefly, the expression for this is 2 times hc, where h, again, is this Planck constant, and this is the speed of light, divided by the wavelength to the power 5, multiplied by e to the hc, divided by kBt, minus 1. Oh, and pardon me, there's a lambda here too. There we go. And so this complicated expression, which is derivable from a statistical mechanics analysis that we're not going to bother to do here, tells us the maximum spectral intensity that physicists tell us is the ideal maximum. Okay? And we can see that it has a very complex dependence on the wavelength, right? There's a wavelength that shows up in this exponent over here, but then there's also this lambda to the power 5. And this expression is what gives us that key quantity that we needed to find, which is the thing that tells us how thermal properties are transduced into electromagnetic energy properties. So, right, this was the Planck constant, this was the speed of light, this lambda is the wavelength, h and c show up down here. This kb is the Boltzmann constant. It was that other physical constant that showed up when we were doing the modeling of ideal gases for free convection. It's the same kb. And this is the temperature. And so this is telling us that the spectral intensity of an ideal emitter changes as the temperature changes too. All right? So what happens if I take this, plug it into this integral, and then just integrate everywhere? Well, one caveat that you have to consider when it comes to analyzing these sorts of systems before we actually evaluate the expression. One thing that you should know is that when we're integrating surfaces, okay, when we are analyzing the electromagnetic energy that's being emitted off of a point on the surface of an object, be aware, right, that that electromagnetic energy can only be emitted outwards, right, away from the surface. And in that case, it actually trims off half of the surface over which, or pardon me, half of the directions over which that electromagnetic energy can be emitted in, right? Because it can go this way, it can go this way, it can go this way, but it obviously can't go downwards because then it's not being emitted. And so whenever you're dealing with calculations that involve electromagnetic, fluxes that are emitted off of a surface and not a point, you have to make sure that you account for changing these angles based off of the fact that, a flat surface can only emit in one hemisphere or half of all of the possible directions. But either way, judiciously performing the integral for this ideal emitter of electromagnetic energy, what we wind up finding is that this Q double prime rad, I'm just going to say ideal over here, that this thing is just this physical constant, which I'll write down in a second, times the temperature of the object to the 4th power. This quantity right here is called the Stefan-Boltzmann constant. It is 5.67 times 10 to the minus 8 watts per meter squared, Kelvin to the 4th power. Now, historically, I have been very loosey-goosey about using Celsius or Kelvin. And the reason for that is because a difference of a degree Celsius and a difference of a degree Kelvin is the same. Okay? The only difference between the Celsius scale and the Kelvin scale is an offset. And that works out because in all of the problems we've worked with so far, we always found that we were working with temperature differences. But this time we're actually working with an absolute value. And because we're working with an absolute value, we have to be very mindful of the units that we use. So this calculation should always take a Kelvin as an input in terms of temperature while we use this value for the Stefan-Boltzmann constant. Okay? Like this version of the equation works only when the temperatures are input in Kelvin. So what are some interesting features of this little equation? Well, one of the very interesting things about it is that notice that the electromagnetic energy flux is now no longer linearly proportional to the thermal property. Before, for conduction or convection, we had noticed that Q double primes were always proportional to the gradient of T or delta T. This time, the dependence is T to the fourth power. And so because radiation is nonlinear, it means that the mathematical analysis of these sorts of problems becomes incredibly more difficult in a way which we will start to observe as we start getting more and more into the kind of complexities of modeling radiation. But for now, we can see the root of what's going to happen, which is that this Q double prime is not linearly proportional to T. Okay. And remember that this is telling us what the heat flux is for an ideal emitter. So what is actually Q double prime rad? Most of the time, at least not from the perspective of like regular, standard engineering problems, we almost never try to find what the actual spectral intensity is. What we do is we try to find the ratio of this to this, of this Q double prime rad to this ideal. Okay? And what we find, right, it's just this divided by this. What we find is that this ratio is a material property, or approximately a material property, that contains all of the physics of the non-ideality of electromagnetic emission. Like all of the physics that we ignored when we assumed that the object was not an ideal black body emitter, all of it gets crammed into this ratio, which we call the emissivity epsilon. And so Q double prime rad, the equation that we most often use for characterizing radiative heat fluxes, which are really just radiative electromagnetic energy fluxes, is just the emissivity epsilon times this sigma times T to the fourth power. And this emissivity is a number that ranges between 0 and 1 and contains all of the physics. So even though this is a more complicated model, technically speaking, of what happens inside of these systems, we actually find that this emissivity is nevertheless still a fudge factor. It's still kind of this thing that hovers around from the perspective of, oh, well, we don't really know what's going on, so we're just going to cram the physics of everything that we don't know into this little fudge factor epsilon, okay? So it's kind of a way, I always like to think of it as physicists trying to hide the fudge, in the sense that, we have always been very clear about the fact that the heat transfer coefficient was just where we dumped all the physics, that the thermal conductivity was where we dumped all the physics. We haven't quite dumped all the physics into the emissivity, but we came pretty close to doing it, right? The only thing that we're actually accounting for here is the ideality of emitters. That we have some understanding, we think, of what ideal electromagnetic emitters look like. And so this is the equation that we use to describe the electromagnetic energy flux off of an object which has some temperature T and some emissivity epsilon. Now there's one last equation that I think is worth describing, and it comes out of trying to understand what the spectral intensity of an ideal emitter actually looks like. And if we plot it on a graph, and this is going to be a horrible drawing, so don't expect anything too accurate here. But if we were to plot the ideal spectral intensity as a function of wavelength, what we would wind up observing is that we would get that, of course, the spectral intensity will vary over wavelengths, that it has this kind of shape where it starts off at 0 for low wavelength, high energy light, grows up until it hits a peak, okay? So it hits a peak at lambda max, and then starts to decay with this long tail as you get further and further out, okay? And the important thing, right, is that this spectral intensity we had seen before varies as a function of temperature. And by extension, this lambda max, this peak wavelength, changes as well. And so as we alter the temperature of an object, we alter the way that it emits electromagnetic radiation. And that is where the color of an ideal black body emitter comes from. It comes from the fact that as I make an emitter hotter and hotter, I can make it such that after a certain point, this maximum wavelength starts getting pushed further and further to the left, all the way up until it hits the visible spectrum. This is why a toaster coil glows red. A toaster coil, when you look at it, in your home, is just black or some other color. That color is usually connected to the light that it reflects, right? So there's very little that it's emitting in the form of electromagnetic radiation from its temperature that would alter its color. As the temperature of the coil starts becoming higher and higher, this lambda max gets pushed from, the infrared all the way up to the visible spectrum, or at least the distribution gets pushed up enough that a non-trivial portion of this peak leaks into the visible spectrum. And because it's going in, right, from large to small, it comes in via the color with the largest wavelength, which is red, which means that your toaster coil, after a certain temperature, as it starts to charge up, starts to glow red. And so black body emitters have a color, which is governed by this lambda max, okay? It's also the reason that magma or lava is red, okay, or yellowish red. It's because it's so hot that the electromagnetic emission from those objects causes it to emit a significant amount of its energy in the visible spectrum, or a significant amount of its electromagnetic energy in the visible spectrum, which usually tends to be focused around red. Now, you can imagine that for things like, say, LEDs, that the spectral intensity of those objects as a function of wavelength is considerably more complex, and that's true. But for the purpose of natural objects, objects which aren't necessarily engineered to emit at specific wavelengths, this understanding is pretty good. And the whole point is that we can use this approximation, which is the equation I was telling you about, called Wien's displacement law, that relates this maximum, this peak wavelength to the temperature of the object in such a way that lambda max times the temperature is equal to 2,898 microns Kelvin. This micron, by the way, is 10 to the minus 6 meters. And so the whole point is that if you know the temperature of the object, you can just take this 2,898 micron Kelvin divided by the temperature and then get the peak wavelength of emission from this hypothetical close enough to ideal emitter in microns. Okay? So again, this only works for stuff that is relatively well approximated as an ideal black body. But it tends to be good enough that we can use it for estimating, say, things like the temperature of the sun. And so this tells us most of the things that we need to know from the perspective of emission. And the next subject that we need to talk about is the process in via which this electromagnetic energy, which is being emitted, then becomes absorbed, or the different ways that that electromagnetic energy can interact with matter, which we will talk about in the next lecture.